Thank you very much for the kind invitation and introduction. So the title of my talk is The Circle Problem, the Divisor Problem, Bessel Series Expansions, and Weighted Divisor Sums. So this is work that I've conducted over the last half a dozen years with Sun Kim and Alexander Zarescu. Sun Kim completed her PhD under my direction and also under the co-direction of Professor Kevin Ford in May of last year. She's now at Penn State on a temporary one-year position and has just accepted a 3-year postdoc at Ohio State University. She's a graduate of Korea University. And Alexander Zarescu is my colleague at the University of Illinois. So these results on which I'm going to speak are motivated by 2 entries in Ramanujan's Lost Notebook. And that statement really should be corrected a bit because they are technically not in the Lost Notebook. So the Lost Notebook was found by George Andrews at Trinity College, Cambridge in the spring of 1976 and was published in 1988 by Narosa in New Delhi. But when they published this Lost Notebook of 138 pages, they also had found over the years some fragments and partial manuscripts of Ramanujan, which they also published with the Lost Notebook. So these 2 entries are actually from just a 1-page fragment that was published with the Lost Notebook. Oyet Chan was also my student. He did the numerical calculations, which I will show you at the end of the lecture. So this person, Viveka Chudamani, in the 6th century, was probably prophetic in speaking about the Lost Notebook here. And the entries in which I will tell you about indeed are mysterious. So I thought I should begin with a picture of Ramanujan. There are only 4 photographs that exist of him, and this is his famous passport photo that was taken prior to his return to India from England in 1919. It looks like he's wearing a suit coat. He's not wearing a suit coat. That's his bathrobe, and he's in his pajamas and bathrobe because he was too ill to go to the photographer to have his picture taken. The photographer had to come to the nursing home where he was residing in order to take his picture. So this information comes to me from Robert Rankin, who was G.H. Hardy's last PhD student. And this is the page in the Lost Notebook that I want to discuss. So please don't strain your eyes trying to read this, because I'm going to tell you in more detail with LaTeX. So I want to concentrate mainly on the first entry. So we'll let f of x be the greatest integer function if x is not an integer, and x minus a half if x is an integer. So in other words, Ramanujan is just averaging out, so to speak, the greatest integer function. And I remind you of the definition of the ordinary Bessel function. In fact, we will only look at the case nu equals 1 in this paper, here in this talk. And here is the first entry on that page that I showed you. So theta is between 0 and 1, x is positive, and I've defined f of x in J1. So Ramanujan states this double series identity. So note that the trigonometric sum on the left-hand side is a finite Fourier series, because if you fix x positive, f of x over n eventually will be 0 for n sufficiently large. So it says then that all the stuff on the right-hand side, somewhat surprisingly, has a finite Fourier expansion. And in particular, note the cotangent, which has singularities at 0 and 1. So there should be singularities at 0 and 1 for this double series of Bessel functions as well. Note that the sum is not quite symmetric in M and N just because of the aberration of theta on the N here. Well, it's not obvious that that double series converges. So I have at the top of the screen here the asymptotic formula for the Bessel functions as x tends to infinity. So the terms in the double series then have this behavior as m and n tend to infinity. So certainly we don't have absolute convergence here, but the 3/4 powers on the m and n seem to indicate we might have conditional convergence. But it will be difficult to show convergence just because the m and n and the trig functions are intertwined together under the square root sign. So indeed, it is extremely difficult to actually show the convergence of this double series. So this identity is connected with the famous circle problem, and I'll indicate later why that's the case. So I'll now explain what the circle problem is, a very famous problem in analytic number theory. So we let R2 of n be the number of representations of n as the sum of two squares. And we count different signs in the sum n's in different orders as being distinct. So if you have 2 squared plus 1 squared, then you can change the sign of the 2 and the 1 in 4 different ways, and then of course you can change the order. So R2 of 5 then would be 8 with this convention. And then each representation of n as a sum of two squares can be associated with a lattice point in the plane. So if you take then 5 as minus 2 squared plus 1 squared, we associate that with the lattice point minus 2, 1. And then with each lattice point, we can associate a square of unit square. So it doesn't make any difference which of the 4 squares we take for a particular lattice point, but we should be consistent. So we'll take the squares such that the lattice point is in the southwest corner. Okay, so then if I look at the sum of R2 of n over all n less than or equal to x, then numerically this is the same as the sum of the areas of these unit squares attached to these lattice points in a circle of radius square root x. So here then would be a picture then. So we've colored red then the squares associated with all the lattice points within the circle of radius square root x. So since the sum of the areas of the squares is equal numerically to the number of lattice points, then the area of the circle should be a good approximation for the sum of R2 of n summed over n less than or equal to x. So we'll let R of x be that summatory function. Note I've included 0 because 0, that lattice point 0, 0 is within that circle. The prime indicates that if x is an integer, we only count half of that term. That might seem surprising to you as to why we should do this, but because of the analysis which arises in examining this problem, it's the more natural sum to look at. Okay, so the number of lattice points in the circle of radius square root x then should be about the area of the circle, pi times x, but there will be an error term, p of x. And the famous circle problem then asks for the order of this error term as x tends to infinity. So the first person to look at this problem was Gauss. So all of these squares are certainly contained within a circle of radius square root x plus square root 2. So pi times square root x plus square root 2 squared would be an upper bound for R of x. But also, if you take a circle of radius square root x minus square root 2, that will be entirely covered red in my previous picture. So pi square root x minus square root 2 will be squared will be a lower bound for this summatory function r of x. And from these inequalities, then you see that r of x is pi x plus big O of square root of x as x tends to infinity. So that's the first estimate that we have for p of x. So the next result that was proved was by Sierpinski in 1904. So Sierpinski, Landau, and Hardy independently discovered this formula for the summatory function in terms of Bessel functions. So p of x then is now represented as an infinite series of Bessel functions. Hardy wrote 2 papers on the subject, and in the first he says that Ramanujan actually informed him of this series. And then in the second paper he actually gives a proof of the result. So Ramanujan then independently also proved this formula, but we know nothing about his proof. And Sierpinski used this identity to show that the error term is big O of x to the 1/3 as x tends to infinity. So since that time, all advances in finding an upper bound for the error term have arisen from this formula of Sierpinski. So what one does is to use the first term in the asymptotic expansion for Bessel functions. So then the problem reduces to estimating a trigonometric sum. So the advances that have been made depend upon advances in estimating trigonometric sums. So I listed here on this screen and the next screen the advances that have been made over the years. So you don't want to look at this too long, but just skim down the left-hand column and you'll see that advances come very, very slowly with just very small advances from one to the next. And then just skimming the right side, you'll see that a lot of people, including very famous mathematicians such as Hardy and Littlewood and the Chinese number theorist Chen, have worked on this problem. So here are the latest results. So the best result that we have at the moment is due to Huxley. So from Sierpinski's initial result to Huxley's, we've improved at about 0.02. This is about all we've advanced in this over a little over 100 years. Well, the problem has also been studied from below. So in other words, try to say that the error term is at least such and such, so such and such large. So maybe some of you don't know the omega notation, so let me just introduce that. So I'll just give one of the 3 definitions. If g of x is a non-negative function, then cap g of x is omega of small g. If there exists a positive constant k, such that the absolute value of g of x is greater than k times small g of x on some sequence of xn's tending to infinity. Not all sequences or anything, but just some sequence. And if we want to keep track of the sign, or if we can keep track of the sign, we have these 2 further definitions. So in the first paper that Hardy wrote, he showed that p of x is omega plus or minus of x to the 1/4. So the error term then is at least a big O of x to the 1/4 as x tends to infinity. But he improved that in his second paper by replacing the x to the 1/4 by x log x to the 1/4. But the improvement was just on the minus sign. The argument didn't work on the plus sign. So I've given 2 further improvements, but these are only improvements on the plus sign, not really on Hardy's result. So these are the 2 latest results that we have. So Jim Hafner, in his PhD thesis at Illinois in 1981, improved Hardy's result for the first time by adding a power of log x, essentially, to Hardy's result. So I should give some credit to Atlee Selberg here, because a few years before, I was at the Institute for Advanced Study, and one day I was talking with Selberg about the divisor problem and the circle problem, and he said to me, I improved Hardy's results some time ago, but I never published them. But in the one or two sentences he described what he had done for his argument. So I remembered these, and then I, a few years later, gave them to Jim Hafner, who then, in further correspondence with Selberg, was able to prove this result. And then 22 years later, Soundararajan slightly improved Hafner's result. So you see, again, the improvements are very, very small. So this is the best that we know about the circle problem at the present. Well, Hardy, in his paper, used this identity in order to prove his omega results. And then at the end of the second paper, Hardy mentions that Ramanujan told him of this result. So it's a very beautiful formula. And note that in getting from one side to the other side, you just interchange the A and the B. So you have to agree that that's a beautiful formula. If you don't think it's a beautiful formula, you don't belong to mathematics, I think. So you can actually get Hardy's result from this by differentiating with respect to B, letting A tend to 0, and then renaming the parameters. So this actually doesn't occur anywhere in Ramanujan's work. Otherwise, it doesn't occur in his notebooks or in any of his papers. But I think this is evidence that Ramanujan was thinking about the circle problem. Well, now let me go back to the first entry on that page in the lost notebook. I've now called it a theorem because just Sun Kim, Zarescu, and I finally completed a proof of this just in January of this year. And before that, Zarescu and I had proved this theorem. So what's the difference between this theorem and the previous theorem? We have reversed the order of summation from what Ramanujan had given. So we're able to prove the result of Ramanujan with the order of summation reversed by actually eliminating the Bessel functions from the identity. So we proved then this equivalent theorem. So you might say, well, why couldn't we have done this with the way Ramanujan had originally stated the theorem? Well, M and N are not quite symmetric in this identity, and it's impossible to, as far as we can see, have an equivalent theorem with the way that Ramanujan had indicated what the summation should be. So this was a little bit easier to work with because we don't have the N and M now under the square root sign, although we've lost the symmetry here in this theorem. Well, what Zarescu and I did is, after we proved that theorem, we proved another theorem in which we introduced characters and L functions. And then as a special case of that theorem, we were able to derive this identity then. Well, you note that these Bessel functions look very much like the Bessel functions in Sierpinski's identity. So we have another representation for the error term P of x, very similar to the Sierpinski representation. But Sierpinski's representation had R2 of n on the right-hand side. Ours doesn't, but ours has a double series rather than a single series. But you might say, well, or guess that these identities should be equivalent. And they are, but I've put the equivalence in quotes. So let me just give you that simple argument and also indicate why the equivalence is in quotes. So just take the right-hand side of Sierpinski's identity and then substitute in Jacobi's very famous formula for the number of representations of n as the sum of two squares. So we substitute in, and I've made a misprint here that should be d is odd instead of k is odd. And then divide up the divisors into two classes according to whether they are congruent to 1 mod 4 or congruent to 3 mod 4. Okay, so substituting in Jacobi's identity, we get this identity, and I just simplified it slightly here. So that's the identity that Zararescu and I proved, but now note that we don't have an iterated double sum, summing on m first and then n, but the m and n are tending to infinity together. So let me just go back to the previous identity. We have set k to be either 4n plus 1 times m or 4n plus 3 times m. So in other words, our upper limit, cap n, is the small m and the small n are tending to infinity together. Okay, so we've shown the equivalence, but with a different order of summation. So not really an equivalence. Well, then the question arises, maybe Ramanujan actually meant his identity to be interpreted in this symmetrical fashion. So I'll call this the symmetrical version of the theorem. So maybe he actually meant the identity, the more general identity, in this sense. Yeah. So Zararescu, Sun Kim, and I have actually proved the identity in this sense as well. So let me just now summarize everything here. So we have three interpretations. We have the iterated double sum, as Ramanujan stated it, and Sun Kim, Zararescu, and I just completed a proof of this in January. And then we could interchange the order of summation. That was a little bit easier, and Zararescu and I did that about 5 or 6 years ago. And then I think it was about last spring that my co-authors and I completed a proof in the symmetric version. So you might ask, can one show the inversion in order of summation directly? And I don't think one can, because the arguments that we used in all three of these interpretations are entirely different. We use nothing from one proof in any of the other two proofs. So to show the inversion in order of summation, I think you essentially have to go through the kinds of proof for each identity. Let me give you just a brief sketch of the proof in symmetric form, and then a sketch and the proof in the way that Ramanujan had stated the identity. So this will bring in the last part of the title of the talk, the weighted divisor sums. So we define these weighted divisor sums, chi of d over d dividing n, where chi is a character modulo q. And this is a Gauss sum. If we take the left-hand side of the identity and replace the sign by a character, then it's not too hard to show that we get the summatory function for these weighted divisors. So again, we call them weighted divisors because if you had chi of d to be identically 1, then we would have the definition of d of n, the number of divisors of n. So what we do is to prove the identity for rational numbers a over q, and then use a continuity argument, which is actually not easy. So we let then theta to be a over q, and we derive this identity for the left-hand side in terms of the summatory function of this weighted divisor, d chi of n. The phi of d here is Euler's phi function. So then the right-hand side, or the double series on the right-hand side, since we're letting theta to be A over Q, has a somewhat simpler formulation now. So we can now think of it as just being summed over residue classes. So here then is the version of the theorem that we would prove when theta is A over Q in the symmetric form. So what we do is to use an identity for the summatory function for the divisor function. So let me ask if any of you have seen this identity. The reason I'm asking this question is that I have not seen it in the literature, but I derived it from a result in my PhD thesis. So you never know when your PhD thesis is going to be really helpful for you. So many years later, then my thesis was more useful than just getting me a PhD and helping me get a job. And then, using that identity, we get another identity for the sums of this divisor function, or this weighted sum, now in terms of a doubly infinite series of Bessel functions. So these are the ingredients that we use in our proof of the theorem in symmetric form. So let me go now to the proof that Zawarescu, Sun Kim, and I have recently given. So this is going to be an oversimplification of the proof, and it's not going to be quite the Fourier series that we need. We're going to use Fourier series here, but it's a little bit, Fourier series is a little bit different than what I'm going to give. By the way, our proof typed up, it runs 36 pages, and it's the longest proof I've ever been associated with in my career. We were exhausted at the end of the proof. So here is an identity. It's not too difficult, but it's not trivial. It's an integral you might give your calculus students. And here's another integral that will need a sine times a Bessel function. And then we need the Fourier series for the sawtooth function, so to speak, or for the first Bernoulli function. So what we do is to let f of theta be everything in the identity except the left-hand side. And we find the Fourier sine series of this function on 0, 1/2. So we just substitute in the familiar formula for Fourier sine coefficients, and we invert the order of summation and integration. And here is where a problem arises, because, of course, not only do we need to know the convergence of this series, we also need to know the uniform convergence so that we can invert the order of summation and integration. So the half comes from the first lemma I gave you, the integral of the cotangent times the sine. And then we just make some simple changes of variable. So these are simple changes, but using the periodicity of the sine, we actually get a very simple, a much simpler formula. And now note the nice thing that's happened. When we sum on n, these integrals just add up, and we just get this infinite integral. And then we can use the second lemma that I gave you. Okay, so now we go back to the BJs, and after using the second lemma, we get this formula for the BJs. And now we realize that we can use lemma 3. This is the Fourier sine series for the sawtooth function. And I've just expressed this in terms of our original function, f. Okay, so now we substitute in the BJs in our Fourier sine series. And then we get the Fourier sine series that we want in the first sum. And then, very conveniently, we get the same, but with a different variable, Fourier sine series for the sawtooth function again. So we use that lemma 3 twice. Okay, and that's the identity that we wanted to prove. but I've swept quite a bit under the rug in this sketch. So I'll tell you a little bit about what we've swept under the rug. So we use the asymptotic formula for Bessel functions. So we look at this series after applying the asymptotic formula. We then handle the terms of the inner sum when m is large. So in this case, m large means bigger than m cubed times log m to the 5th power. And then we also handle the terms when m is small in this double series. Then we break up this series into two further series, and with a little bit more work, we can handle the terms where n is bigger than m to the 1 plus delta. Delta is a positive number that we determine at the end of the proof. I think it turns out to be 2 over 69. Okay, this is just a substitution just to make the terms a bit easier. Okay, so it comes down to looking at this sum. And here we've just used trigonometric identity for the difference of two cosines. And then we have to break the sum up. I'll skip that. And then we use Cauchy's criterion. So it boils down to looking at this kind of double sum. And again, the delta has to be determined later. Then we have to break this up into very small rectangles and look at them of size t to the lambda, where lambda is a positive number that has to be chosen later. And then we have to separate out the cases when x is an integer from when x is not an integer. When x is not an integer, the argument is a bit easier. So the problem then really boils down to, and this is the hardest part, where xm over n and xn over m are close to integers. So this causes the most difficulty. Then we estimate the double series by a double integral, and we evaluate the inner integral easily, and this is the outer integral, and I should have actually written this before. This is the sum that we eventually get. Well, this integral is 0. And this comes from just breaking this up into two integrals by the addition formula for the sine. So these are elementary integrals. And if this integral were not 0, our method would have failed, because we wouldn't get something which goes to 0 as t tends to infinity. So sort of a miracle happened at the end. We didn't realize as we began all this analysis over some months that we would depend upon this integral being 0 at the end. And that 3 pi over 4 is crucial. If I had pi over 4, I wouldn't get 0 in the integral, and everything would just go to pieces. So this 3 pi over 4 arises from the asymptotic formula for Bessel functions that we used at the beginning. So we considered ourselves to be very lucky at the end of the proof. Okay, so that is the first of the two identities. And let me just say one more word about the identity. So often in analysis, if you have a formula with additional parameters, hopefully the additional parameter will help. So here then we have a formula with two parameters, the theta and the x, and hopefully, but we have no idea now, this will be helpful in the circle problem. So we think indeed Ramanujan saw this, that he was going to use this for the circle problem, but we have no idea what his thoughts are. He didn't leave us any more information. So let me go to the second identity, which is connected with the very famous Dirichlet divisor problem. So I'll tell you about the divisor problem first. So d of n is the number of positive divisors of n. And then the problem is to estimate the sum of d of n over n less than or equal to x. And that prime on the summation is there for the same reason as before. The analysis that one uses naturally gives us this sum. Well, the main terms are x times log x plus 2 gamma minus 1, where gamma is Euler's constant. That 1/4 there just arises from the analysis. It's a very harmless thing, but when discussing the error term using the analytic techniques, it sort of arises there. And, so we put it in, don't include it in the error term. So delta of x is the error term, and the famous Dirichlet divisor problem then asks for the order of this error term as x tends to infinity. And almost every advance that's been made on the circle problem then has a corresponding advance on the Dirichlet divisor problem and conversely. Okay, so let me just briefly indicate how Dirichlet derived the main terms in the estimate for the divisor problem. So this is just a simple exercise of inverting the order of a summation here using the definition of d of n as the sum of the number of divisors of n. Okay, so from that previous representation, you can see that the summatory function of d of n then is equal to the number of lattice points under this hyperbola yz equals x. Because, maybe I'll just go back to that, you see we're actually then summing then lattice points on vertical lines then under this hyperbola yz equals x. So the way Dirichlet argued was this: we'll not only sum on vertical lines, say in regions 1 and 2, but we'll stop at square root x, and then sum on horizontal lines, stopping at square root x. So we've then covered then the lattice points in region 1 twice, then in this way. So we have then the lattice points for regions 1 and 2, and then for 1 and 3, and then of course, sorry, I was looking at the wrong ones here, and then we subtract off those lattice points in region 1. And now we just replace the square brackets function by x over d with an error of at most 1, and curly brackets x is the fractional part of curly bracket square root of x is the fractional part of square root x. Now I just simplify here and use the fact that the sum of the big O of 1s is just big O of square root of x. And this is easily seen. And now we use a familiar formula for summing a partial sum of a harmonic series. So that's log square root of x plus gamma plus this error term, and now you just simplify what we have. So that's Dirichlet's argument, and the first estimate that we have then, big O of square root x for the Dirichlet divisor problem. So the first person to make an advance on this after Dirichlet was Voronoi in 1903. So I'll use Ramanujan's notation. I nu of z is minus y nu minus 2 over pi k nu. So these are Bessel functions of the second kind and modified Bessel functions. So you don't really need to know much about Bessel functions. So what I'll give you the asymptotic formula shortly. The y one behaves as infinity, much like the j one. And then Voronoi showed that the error term delta of x has this representation in terms of Bessel functions. And he used this representation for the error term to show that delta of x is big O of x to the 1/3 log x as x tends to infinity. And since Voronoj's paper, all advances on the Dirichlet divisor problem have depended upon this formula of Voronoi. Again, what one does is to use asymptotic formulas for the Bessel functions, and then estimate trigonometric sums. So now let me give you then Ramanujan's second identity. So it involves f of x again. So now on the left-hand side, we have a finite Fourier cosine series instead of a sine series. And we have an infinite sum of Bessel functions again, but now they're I1 instead of J1. And then these functions are also a little bit different then. And note that 1/4 here. Okay, so this turns out to be harder to prove than the first one. So here are the asymptotic formulas for the Bessel functions. Note that k nu tends to 0 exponentially as z tends to infinity, so we can really ignore that in our analysis. So why does this problem, why is it a bit more difficult? Well, k nu and y nu have singularities at the origin, and these cause problems. So the Fourier cosine series method does not work. We get divergent series if you use the kind of argument that I gave before, but just in the past couple weeks, we've actually now corrected this. In other words, we now see how we can use Fourier series. So we think we've overcome this hurdle. So a problem that arises also is that there is no cancellation in the pairs of Bessel functions. You probably didn't notice this, but for the first identity, I had a minus sign between the Bessel functions. And that cancellation seems to help the convergence. In this identity, we have a plus sign between the Bessel functions, and that does seem to slow up the convergence quite a bit. In fact, for a couple years, we thought that the result was false because it didn't seem like the double series was converging. Well, Zararescu, Sun Kim, and I first proved the identity with the order of summation reversed. And so we derived an equivalent identity, again involving trig functions, but as you can see, it's much more complicated than the trig function identity that I gave you earlier. And you'll get dizzy looking at this identity, but just know one thing, and that is I have the sums intertwined with the integrals together. And that is important. I have to look at the limit of the difference of those. So, as I indicate here, the individual series and integrals diverge by themselves, so that's why we have to put them together. I've reversed the order of summation, and in the theorem that we have proved, we have to assume that the double series converges at one value of theta. If it converges at one value, then it converges for all values between theta between 0 and 1. Now, Zararescu and I sort of have a difference of opinion here. He likes this theorem much better than if we had a theorem where we didn't have this hypothesis, that we have convergence at one value of theta. He said, and he's correct, there doesn't seem to be any theorem in the literature like this. So it's a new kind of theorem in the literature, so he likes this better. Whereas I prefer that, we've proved the identity, without this additional hypothesis. Okay, so we do have the identity then with this additional assumption proved, but with the order of summation reversed. Okay, so let's just summarize what we have here. We do not have a proof yet of Ramanujan's identity as he originally stated it, but I think now we've overcome the last hurdle, and hopefully in a couple months we'll have a proof. We have proved, as I indicated, the formula with the order reversed, but we have this additional assumption. And we actually also have proved the theorem if we interpret the double series in a symmetric notation. So we've now done it in 2 out of 3, but with the additional hypothesis on part B. So let me just give a few numerical calculations to show you that this double series seems to converge very slowly. So L of x theta is everything in the identity except the double series, and the R here is a partial sum or partial sums of the double series. So here are just a few numerical calculations. So let's just look at those in the top three here. So we want these partial sums to tend to 0.09657. But note that at 1,000 terms, we're worse off than we were at 500 terms. So, that doesn't look very good as far as convergence. For other values, things are a little bit better. So if you look at the third group of 3, we're doing a bit much better on that for those values of m and n. And now I've sort of switched things around and made n large instead of m. And again, if you look at the first 3, we were better off at 500 terms than we were at 1,000 terms. Okay, so because of these calculations, for a couple years we thought that maybe there was a missing term or something in the series, but now we're convinced that Ramanujan was correct. We should have never doubted Ramanujan. Bad practice to doubt him. So. Well, we were able to sort of use our methods to get a few further identities. And so there are actually some further problems that we're now posing which are similar to the classical circle and divisor problems. So we have, for example, this identity for a sum of 2 cosines summed over nm less than or equal to x. So theta and sigma are both between 0 and 1. So it seems to be very hard to estimate a sum of this type, and we have an identity now in terms of actually 4 Bessel functions. And to prove such an identity, and we've proved it only in the symmetric version, but we think our proofs would work in the second version that I just gave you before, we use these further weighted divisor sums. So here we now have 2 characters in our weighted divisor sum, and we need an identity for the summatory function of these weighted divisors. So I'll ask the same question I asked you before. Please tell me if you've seen this identity in the literature. Again, I derived this from a result in my PhD thesis. So then in the symmetric version, it reduces to just this kind of identity, which is a bit simpler. So now we're summing over residue classes because we've let theta be A over P and sigma be B over Q. And then we have further identities, which I won't go into, for a cosine times a sine. And it happens that the n and m sort of appear here. It's a bit unnatural, but that's just the way the analysis rose. But so I think that hard problems exist for estimating these sums, just like they did for the circle and divisor problems. So I think that concludes everything that I have to say, and I'm sorry, Ramanujan, that I doubted you on the second identity. So thank you very much.